Water pipe grounding details are addressed in the National Electrical Code, specifically in Section 250.104(a)(5). This section outlines the requirements for bonding metal water piping systems. The International Residential Code, or IRC, also covers this topic in Section R314.23. Service grounding details are covered in NEC Section 250.24 and IRC Section R314.21. Now, let's discuss what information should be included in these details. Firstly, the size and material of the water pipe used for grounding must be specified. This is crucial because the pipe must be capable of conducting fault current safely. Copper and steel are common materials, and the pipe's diameter impacts its conductivity. Secondly, the location of the water pipe connection to the grounding electrode system needs to be clearly indicated. This connection must be accessible and made with approved methods, such as grounding clamps or exothermic welds. The grounding electrode system typically includes the water pipe, ground rods, and other electrodes. Thirdly, the size and type of grounding conductor are essential details. The grounding conductor connects the water pipe to the electrical service equipment and must be sized according to NEC Table 250.122, based on the size of the ungrounded conductors. Common grounding conductor types include copper and aluminum. Fourthly, the location of the connection to the electrical service equipment must be specified. This connection is usually made at the service entrance, where the grounding electrode conductor is connected to the neutral bus or grounding bus. Fifthly, the bonding of other grounding electrodes, such as ground rods, to the water pipe is an important detail. This bonding ensures that all grounding electrodes are connected to form a comprehensive grounding system. The utilities detail may be sufficient if it encompasses all of these aspects. However, it is crucial to verify that the utilities detail complies with the latest edition of the NEC and local codes. If there are any discrepancies, it is essential to address them to ensure compliance. Now let's consider some additional resources that can be helpful. The Electrical Grounding and Bonding Handbook by Mike Holt is a comprehensive guide to grounding and bonding principles and practices. This handbook covers a wide range of topics, including grounding electrode systems, equipment grounding, and bonding of metal parts. The Grounding and Bonding for Electrical Installers, published by the Associated Electrical Contractors, or EEC, is another valuable resource. This book provides practical guidance on grounding and bonding techniques for electrical installations. The NEC Grounding Handbook by Don Zimmerman is a useful reference for understanding the NEC requirements for grounding and bonding. This handbook includes explanations of the code rules, examples of compliant installations, and illustrations to clarify complex concepts. Let's discuss the importance of proper grounding. Grounding provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection device, such as a circuit breaker or fuse, and clear the fault. This protects people and equipment from electrical shock and damage. Bonding is also essential for electrical safety. Bonding connects all metal parts of the electrical system to the grounding electrode system, which minimizes voltage differences and reduces the risk of shock. Now let's talk about some common grounding mistakes to avoid. One common mistake is using undersized grounding conductors. The grounding conductor must be sized according to the NEC to ensure that it can safely carry fault current. Another mistake is failing to properly bond metal water pipes. Metal water pipes must be bonded to the grounding electrode system to prevent them from becoming energized. A third mistake is using improper grounding methods. Grounding connections must be made with approved methods, such as grounding clamps or exothermic welds. A fourth mistake is neglecting to inspect and maintain the grounding system. The grounding system should be inspected regularly to ensure that it is in good condition and that all connections are tight and corrosion-free. Now let's discuss the different types of grounding electrodes. The most common types of grounding electrodes are metal water pipes, ground rods, and concretely encased electrodes. Metal water pipes must be in direct contact with the earth for at least 10 feet to be considered a grounding electrode. Ground rods must be at least 8 feet long and driven into the earth. Concrete encased electrodes must be at least 20 feet long and encased in at least 2 inches of concrete. It is important to select the appropriate grounding electrode for the specific application. Now, let's talk about the requirements for grounding electrode conductors. The grounding electrode conductor connects the grounding electrode to the electrical service equipment. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The grounding electrode conductor must be continuous and unbroken. Now let's discuss the requirements for equipment grounding conductors. Equipment grounding conductors connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. This includes equipment such as metal enclosures, motor frames, and appliance chassis. Equipment grounding conductors must be sized according to NEC Table 250.122, based on the size of the overcurrent protection device. Equipment grounding conductors must be installed in the same raceway or cable as the circuit conductors. Now let's talk about the importance of grounding in sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, requires special grounding to protect it from damage. This type of equipment typically requires a dedicated grounding conductor that is isolated from the normal equipment grounding system. The dedicated grounding conductor provides a low impedance path for noise and transient voltages to return to the source, which helps to prevent damage to the equipment. Let's consider surge protection. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. SPD are typically installed at the service entrance and at branch circuits to protect sensitive electronic equipment. SPD work by diverting surge current to ground, which prevents it from damaging the equipment. Now let's discuss the importance of documentation. It is essential to document the grounding system to ensure that it is properly maintained and that any modifications are made correctly. The documentation should include the location of the grounding electrodes, the size and type of grounding conductors, and the methods used to make the grounding connections. The documentation should also include a diagram of the grounding system. Now let's address the need for periodic inspections. The grounding system should be inspected periodically to ensure that it is in good condition and that all connections are tight and corrosion-free. The inspection should include a visual inspection of the grounding electrodes, grounding conductors, and grounding connections. The inspection should also include testing of the grounding system to verify that it is providing a low impedance path for fault current. Now let's discuss the importance of training. Electrical installers should be properly trained in grounding and bonding techniques. Training should cover the NEC requirements for grounding and bonding, as well as the practical aspects of installing and maintaining grounding systems. Training is essential for ensuring that electrical installations are safe and compliant with the code. Let's consider the role of the electrical inspector. The electrical inspector is responsible for verifying that electrical installations comply with the NEC and local codes. The electrical inspector will typically inspect the grounding system to ensure that it is properly installed and that it meets the code requirements. The electrical inspector may also require testing of the grounding system to verify that it is providing a low impedance path for fault current. Now, let's address grounding in existing buildings. Grounding in existing buildings can be challenging, especially if the original grounding system is not up to current code. In some cases, it may be necessary to upgrade the grounding system to meet the current code requirements. This may involve installing new grounding electrodes, replacing undersized grounding conductors, and bonding metal parts of the electrical system. Now let's consider the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in the circuit conductors and tripping the circuit if there is a difference of 5 mA or more. GFCIs are required in certain locations such as bathrooms, kitchens, and outdoor areas. GFCIs do not replace the need for proper grounding, but they provide an additional layer of protection. Let's talk about the differences between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects all metal parts of the electrical system together. Grounding provides a low impedance path for fault current to return to the source, while bonding minimizes voltage differences between metal parts. Both grounding and bonding are essential for electrical safety. Now, let's address the issue of corrosion. Corrosion can damage grounding electrodes, grounding conductors, and grounding connections. Corrosion can increase the impedance of the grounding system, which can reduce its effectiveness. It is important to protect grounding components from corrosion by using corrosion-resistant materials and by applying protective coatings. Let's discuss the impact of soil conditions on grounding. Soil conditions can affect the effectiveness of grounding electrodes. Sandy soil and rocky soil typically have higher resistance than clay soil. In areas with high soil resistance, it may be necessary to install multiple grounding electrodes to achieve the required grounding resistance. The National Electrical Code, or NEC, provides requirements for grounding and bonding to ensure electrical safety. Water pipe grounding and service grounding are critical aspects of a comprehensive grounding system. The utilities detail might suffice if it provides the necessary information on the size and material of the water pipe, the location of the connection to the grounding electrode system, the size and type of grounding conductor, the location of the connection to the electrical service equipment, and the bonding of other grounding electrodes. Remember to consult the NEC and relevant resources for detailed guidance. Firstly, make sure the water pipe is metallic and makes direct contact with the earth for at least 10 feet. Secondly, use a grounding electrode conductor sized according to NEC Table 250.66 to connect the water pipe to the service equipment. Thirdly, supplement the water pipe electrode with an additional electrode, such as a ground rod or ground ring. Fourthly, bond the water pipe to the other electrodes to create a low impedance path for fault current. Fifthly, protect the grounding connections from corrosion. Sixthly, inspect the grounding system regularly to ensure it remains effective. Seventhly, always refer to the latest edition of the NEC and local codes for specific requirements. Eighthly, consider consulting with a qualified electrical contractor for assistance with complex grounding installations. Ninthly, ensure that all grounding connections are accessible for inspection and maintenance. Tenthly, document the grounding system to facilitate future maintenance and modifications. Grounding and bonding are essential for preventing electrical shock and ensuring the safe operation of electrical systems. These details are important for the electrical inspector.